So I'm primarily a scientist, an experimental scientist. So I'm governed by data. I'm not worried about economy or politics or anything else like that. So what we did in the Centre for Environmental Research and Earth Sciences is that we analysed all the data from 20 million radio sondes and said, what does this tell us about climate change? Now, the Endangerment Act is based on the assumption that the greenhouse gases produced by human beings is heating up the atmosphere. And so we looked and said, what's the weather balloon data telling us about this? The other thing is they say that this is proved by the climate models. So all of the climate models that you see are based on dividing the atmosphere into little boxes. So the general size of the grids are about 1,000 miles long on horizontal, but only about a mile high on a vertical scale. And the assumption that they make, which is key to proving the radiative forcing technique, is that each of those boxes, the air in each of those boxes is in thermodynamic equilibrium within the box, but that the different boxes are not in thermodynamic equilibrium with each other. And they assume that on a horizontal scale, the atmosphere is in thermodynamic equilibrium over the 1,000-mile scale, but on a vertical scale, it's only in thermodynamic equilibrium for about a mile. And this turns out to be a major mistake. And the reason is that if the atmosphere from the ground up the 20 miles or so that contains 99% of the atmosphere is in thermodynamic equilibrium, then Einstein showed 100 years ago that under those circumstances, the rate of absorption of radiation would be equal to the rate of emission. In other words, there would be no greenhouse effect. So how do we determine, what do we mean when we say something's in thermodynamic equilibrium? Well, what we mean is that the net change in energy within the system is zero, and the net change in the different types of energy within the system is also zero. Now, how can we determine whether something is in thermodynamic equilibrium or not? And if it turns out that each of these boxes are able to maintain thermodynamic equilibrium with each other, which the balloon data is showing, and I'll show you why in a moment, then the whole basis of the greenhouse effect is gone. So to determine whether something's in thermodynamic equilibrium or not, what we do is we take the thermodynamic system and we measure all the different parameters that characterize the system, pressure, volume, and so on. And if we can then characterize the system and it obeys what we call an equation of state, then we say the system is in thermodynamic equilibrium. Okay. So this is the equation of state for air. This is the one used by the climate modelers. And you can see the relationship between the pressure, the temperature. The N is the number of molecules, and T is the temperature. And there is R is a gas constant. It's the same for all gases. So just to explain, climate modelers and atmospheric scientists divide the atmosphere into different layers based on how the temperature behaves. So in the lower region, which is called the troposphere, that describes the area where the temperature drops off in a more or less linear fashion as you go up through the atmosphere. And this has been known for hundreds of years. Since they invented the thermometer, people could go up mountains and measure this lapse rate. But about 30 years before I was born, they then got the quality of the balloons good enough to go up higher. And then they discovered that that this didn't go on forever, as people had assumed. Instead, the temperature stopped rising, or stopped falling, and might have risen slowly or continued reasonably stably along. When they first started doing this, they thought their thermometers were broken, and they went to a lot of trouble to prove that they weren't. But then when you get higher up, the temperature starts to rise again, and this is called the stratosphere. Now, if we get back to the equation of state, it turns out that there's more than one form of the equation of state. The one on the left-hand side is called the energy form, and the units of that is joules. But there is another form of the equation of state, and that's called the molar density form. It's got by rearranging the order of the particle of the parameters. But this molar density form has been used by chemists for over 100 years to determine the molecular weight of gases. And what we did, which nobody else had done before, is we said, what if we used this form to describe the behavior of the atmosphere? And what we did when we did that was we got a big surprise. Because if you plot the pressure versus molar density, what you get is, in the troposphere, the lower section of the atmosphere, you get a dead straight line, except for a little kink, I don't know if you can see it there, where the balloon traveled through a cloud. But then at the tropopause, it turns into another straight line. Now, chemists and physicists, when they see this, so what this means is that in the tropopause, we can get an equation of state that explains what's happening to the tropopause. The tropopause obeys this equation of state, and then, sorry, the troposphere does. And then above the troposphere, the tropopause obeys a different equation of state. And when chemists or physicists see this, what they call it is a phase change. So when something is obeying one equation of state, it's one phase, and then it changes to another phase. Now, this isn't just unique to that radiosonde. We looked at all the different radiosondes, millions of them, and what we found was they exhibited the exact same behavior, but that the position at which the phase change occurred was higher in the tropics, where the tropopause was warmer, and lower in the polar regions, where the tropopause is colder. And so, to me, that tells me that the atmosphere is in thermodynamic equilibrium, but I don't expect you to take that away from this slide. Instead, what happened was myself and my son Ronan were asked to give a talk in Tucson in 2019, and we took the entire year's radiosonde data for Tucson, and we plotted the molar density form on one side and the normal temperature form on the other side. So the black dots will show the actual measured data. And so if we're looking and trying to see if the atmosphere can maintain itself in thermodynamic equilibrium, then what that means is if we were to take one of those little boxes and put a pile of energy into it, then if it's in thermodynamic equilibrium for all of the boxes, there would be a synchronized change. All of the boxes would change in a synchronized way to reflect the change in one of them. If it wasn't in thermodynamic equilibrium, that wouldn't happen. So I'm now going to let you see the video, which we condensed the entire year's data into just 1 minute. But what I want you to notice is, when you're looking at it, is that when the troposphere heats up, that boundary moves upwards. And when the troposphere cools down, that boundary moves downwards. And at the same time, you'll notice the little orange line there in the temperature one. That'll help you to see what's happening above in the tropopause. So when the troposphere heats up, the tropopause cools down, and when the troposphere, and vice versa. And it all happens in a perfectly synchronized way. So you'll find that the line jumps up and down every few days, and sometimes it jumps huge amounts. What you'll see is that the whole thing is perfectly synchronized, and it shows that the atmosphere is in thermodynamic equilibrium. From ground, all those 20 boxes are all thermodynamically connected. But the second assumption I want to look at here is for hundreds of years, the scientists have been trying to explain how the wind blows and why we have trade winds and why we have the doldrums and why the Sahara is a desert and so on. So they came up with this idea of these circulating cells. They're called Hadley cells, Ferrel cells, and polar cells. The reason is that if you look at the tropics, there's a lot of hot sunlight lands in the tropics, but the amount of energy coming in the tropics is less than the amount of energy radiated out. But in the poles, there's more energy radiated out than actually comes in from the sun. So obviously there's some transport mechanism taking the energy from the equator to the poles. So before I go on a little further, I just want to explain what we mean by mass flux. So it turns out that all the radio balloons measure at each of the levels that they take it, they measure the wind speed and the wind direction as well. And using the molar density form of the equation of state, we can actually calculate the weight of the air at those points as well. So we can actually calculate the mass flux, which is the weight of air traveling through any surface. So we can resolve the mass flux into a north-south component because it's a vector quantity there. And so we can actually use the weather balloon data to check the mass flux. So if you look at the Hadley cell and the standard explanation, George Hadley in 1737, I think, came up with the idea that the hot air landing on the tropics heated up the air there, and that air then rose, and in rising up it created a vacuum which pulled in the extra air. But it created a pressure up higher, and that pressure then is moved towards the poles. And as it moves, it gets colder and then sinks down, and you get this circulated pattern. Now, what we did is we said, let's see what the weather balloon data say, because it's easy to check. And again, surprisingly, nobody has ever bothered to check to see if what you'd expect would happen. And what you'd expect there, the little diagram on the side, is that if you measure the mass flux at the ground level, it should be going towards the equator. And then as you go on up, at some stage or other, it'll flick over and start moving towards the poles. And the amount of mass flux in one direction at the equator has got to be matched by the amount in the poles. So when we looked at the weather balloon data, we actually found nothing like that at all. So this is, the one that we did in Iceland, looking at the polar cells. And if the theory was correct, the blue and dark blue and light blue lines should be moving in the opposite direction to the yellow and orange lines, because one's in the top of the atmosphere and the other's in the bottom. And we don't find that at all. Instead, they all move in the same direction. So the atmosphere is moving back and forward like a giant pendulum, and not in the circular motion that you would expect. And so we did the same for the other cells, and we find the exact same result. Now, some people have said then that maybe that's because on average over the year, the cells work, and so on a day-to-day basis, maybe they don't. But we averaged the data over the whole 5 years for each of these stations. And up on the one there for Iceland in the top, you can see on average the atmosphere is all moving south. The one for Ireland, which is in the Ferrel cell, that again is moving south. But the one in Spain, which is also in the Ferrel cell, that's moving north. The one in Morocco is doing crazy sort of things. But just look down at the one in Mauritania, which is in the Hadley cell. And then you say, that at the ground level is moving in one direction, then it flicks and moves to the other direction. But the problem is that it's moving in the wrong direction, because it's at ground level it's moving north. So that's actually an anti-Hadley cell. So that was as far as we published in those papers there. But since then, we then analysed 250 of these stations in the tropics. And what we found is the majority of them were either anti-Hadley cells or, like the Iceland one, all moving in the one direction. But it was even the ones that were Hadley cells, it turns out that the direction moving in the ground level was only a fraction of the amount moving in the upper level. So what we have shown is that the Hadley cells, circulation models, all of those don't actually exist at all. So in summary, what we're saying is the balloon data shows that the whole atmosphere, all the different cells, all those different boxes from top to bottom, all behave in a synchronized way and are in thermodynamic equilibrium and not as the radiative forcing models say. And in other words, when the climate modelers do their models, they were quite proud that they were able to reproduce the Hadley cells, but they don't exist.